In this video, we will be understanding logs and how to use them to solve exponential functions. The logarithmic function f with the base of a is denoted by y equals log base a of x if and only if x is equal to a of y, or a to the y power, where again a is positive and a cannot be equal to 1. So for example, you can rewrite this log function by taking the base, raising it to this exponent, and then that will equal what is on the inside, which is 81. Same thing here. If you take the base, raise it to what the function is equal to, and then that will be equal to what is on the inside. Again, the base, raise it to what is on the outside, and you set that equal to what is on the inside. You can work backwards as well, so you can rewrite this as a log. So this would be written as log base 5 of 125 equals x. Again, remember, just like you had the base raised to the exponent, 5 raised to x means x goes on the outside. Same thing here. You would have log base 2. So 2 was raised to an x, so 2 should be raised to the x, and that should equal 41. So you can go back and forth between the exponential functions and the logarithmic functions. The log graph and the exponential graph are actually inverses of each other. So 2 to the x in a previous video we discussed is this graph right here, which is in green. The log of base 2 is this graph, and they basically, you could say they are a reflection of each other across the line y equals x. So if you think about a diagonal reflection, these are actually inverses of each other. So where this graph crosses at 0, 1, this graph crosses at 1, 0. The x and the y flip-flop each other. Log properties. So the log base 10 is represented by log of x, and that is called the common log. So if you do not have a base that is written, it is understood to be the number 10. Log base a of 1 is 0, and the reason is because any number raised to the 0 power is 1. A raised to the 1 is also going to equal itself, and so a to the 1 is a. Log base a of x equals x, because if you were to rewrite this, a raised to the x is going to equal a to the x. And then if you have two equations that have the same log base and they're equal to each other, then the insides are going to be equal to each other. Since log base a of x equals log base a of y, that means x and y must have been equal. So evaluating logs, in this case, you can do this without a calculator. So you could say 2 raised to the what gives you 16. And the answer is 4. Because 2 to the 4th power is 16. Log base 3 of 9. So you're asking yourself, 3 raised to the what is going to give me 9? And the answer is 2, because 3 squared is 2. 3 squared, is 9. 3 squared is 9. So therefore you would say that log base 3 of 9 is the number 2, because 3 squared is 9. Same thing up here. 2 to the 4 equals 16. So log base 2 of 16 will equal 4. This does not have a base, so it's automatically assumed to be a 10. So 10 raised to what power gives you 100? And again, the answer is 2. Because 10 squared is 100, so you could say that log of 100 equals 2. And then in this case, you're thinking 2 raised to the what equals 1/8. So if you remember back a long time ago that talked about exponents, you could say 2 raised to the what equals 8 to the negative 1. If you think about the fact that a fraction is basically that number raised to a negative power, So your answer is going to be -3 because 2 to the third equals 8. So therefore 2 to the -3 is going to give me 1/8. Now to do it with a calculator, the way you would do it is called a change of base. So to find the log base 4 of 27, you would do log of 27. You must close the parentheses and then do log of 4 and then hit enter, and that is your answer. So log base 4 of 27 is 2.377. So if you think about it, 4 raised to the 2.377 is going to give you 27. Which should work out nicely if you think about the fact that 4 to the second power gives you 16, and 4 to the third power gives you 64. So you know that 27 happens in between 16 and 64, so you know the answer has to be between 2 and 3. Now obviously 27 is closer to 16, and so that's why your answer should be somewhere a number that is closer to 2, which is 2.377. The next one, you would do log base 10, or log of 10. Oops, I didn't hit the parentheses. You must use the parentheses. Divided by log of 5. And your answer would be 1.43. Log of 42, you can just type in log of 42. And you'll get 1.6. And then log of 4. So 112. So what you would do is log of 1 divided by 12, close the parentheses, divided by log of 4. And that will end. You should get a negative because 4 raised to a power that creates a fraction should be negative, because 4 raised to a negative power is what flips it to make it a denominator. So you should get a negative in the last case. The logarithmic function defined by log base e is actually called the natural log function. So for example, this natural log basically has an understood e as a base, so it would be e raised to the 5th power, and that would equal the inside, which is x. Same thing. The natural log has an understood e, so it'd be e raised to the 1/4, and that would equal what is on the inside. So just like log of x has an understood 10, natural log of x has an understood e. From exponential back to natural log as well. So you would say the natural log of 5 equals x. Again, it's because it's an understood e raised to the x, which it was, and that equaled 5. And then the next one, same thing. It would be natural log of 14 equals x. And like we just talked about, the fact that e to the x and the natural log of x are inverses of each other. They are inverses. So if you think about, again, the fact that they mirror each other across the line y equals x. And so that is why you're able to rewrite exponential functions and natural log functions and log functions. You can be able to go back and forth to be able to solve equations with them. So natural log properties are very, very similar to the log properties. The natural log of 1 is 0 because e raised to the 0 power equals 1, because any number to the 0 power is 1. The natural log of e is 1 because if you think about the fact that the base is e, so e raised to the 1 equals e. The natural log of e raised to the x is x because if you think about this is the base of e. So e raised to the x is going to equal e to the x. And then if the natural log of x equals the natural log of y, that means the inside's numbers must also equal, x must equal 1. You can evaluate this with a calculator as well, very simply by plugging in the natural log of 0.5, and you will get a negative 0.693. In this case, you can do 3 natural log of 50, and you will get 11.7. And then natural log of a negative 5, if you plug that in, you will actually get an error. And the reason is because you cannot take the natural log of a negative number. So if you look previous back, this is the natural log, and we tried to plug in a negative 5, which is over here. The natural log never crosses the y-axis as a parent function. So therefore, you cannot actually find the answer to that. That's why it is an error. So we can solve basic log equations by rewriting them as an exponential function. Now in this case, we do not have to rewrite it as an exponential function because we have already solved for x. So we actually can just take and use the calculator and take log base 7 of 343, and we actually get the number 3. Because 7 to the 3rd power is 343. In this case, we have x that is inside the log. So in order to get it out, we can take x, raise it to the 4th power, and that is going to equal the inside number of 81. And now, the way we solve for x is we can take the 4th root of x, and we will get 3. Now, in the past videos, we've discussed taking square roots, and it's always plus or minus. The reason we cannot do plus or minus here is because when we're looking at the graphs, we do not have negative x's. The graph does not cross the y-axis, and so the answer is only going to be a positive 3. Log base 2 of x, we need to get x by itself, so we need to get it out of the log, so we are going to rewrite it as an exponential function. So this would be 2 raised to the 7th power equals x. And now that we have x by itself, we can now do 2 7th power, which is 128. This one over here, x is trapped inside the log, so we need to rewrite it as an exponential function. So this would be x raised to the negative 3, and that's going to equal 1/8. So if you think about x being raised to a negative number, this is the same thing as 1 over x to the 3rd equals 1/8. So what number to the 3rd power is going to give you 8? And the answer is 2. And last, x is trapped inside the log, so we need to rewrite this. So it's going to be the base raised to the 3/2, and that is going to equal the inside, which is x. So 64 raised to the 3/2. There's a couple ways you can do this. One, you can just use the calculator. 2, you can rewrite this. 3/2 means it's the square root of 64 to the 3rd, because the 2 in the denominator means the square root. So you can say the square root of 64 is 8, so 8 to the 3rd power is 512. So there are more complex log functions that can still be written as an exponential function. So what we are going to do at this point is we're going to rewrite this as an exponential equation without solving it. So if we use the same concept, we will take the base, which is 5x. Now, why did I use a parentheses? Because both the 5 and the x are in the base. If you don't use parentheses, then you're not making both the 5 and the x being raised. So the base, right here, 5x, is being raised to the outside number. So that would be 3x plus 2. And then that should equal this inside number, which is 2x minus 4, which worked. So let's do another one. This is a natural log. So to rewrite this, the natural log, remember the base of a natural log is e. So this is e raised to the outside, which is 3x plus 1. And that should equal the inside number, which is 4. And it worked. Last one, we have a base, which is x minus 8, and that is being raised to the outside number, which is 3x minus 3, and that whole thing should equal the inside, which is x.